This call is not recording. All right, recording. Okay. So welcome back to my YouTube viewers. So today we will be doing continue on computing for limits. Okay. So last time we did discuss on the ones where we covered in our foundation, which is this. But there are a few newer concepts, squeeze theorem. Then we have limits for trigonometry. But if it's in indeterminate form, when we directly substitute the the values into our function. So that is what we will be discussing today about those special limits where we have to use um, the properties of the simple limits such as line plot, limit as x approaches 0 for sin x over x. Okay, so give me a few minutes, I mean not a few minutes, just give me a few seconds to find the questions which I need to for this session. Anyways, for those from YouTube, right? Have an if you have a question to ask, you may ask it in the comments tab, or if you found any minor mistakes or error in my calculations, please do let me know so that I can tell the viewers lah in the near future about my previous calculations. So I will not touch questions that has something to do with theory, but which is very important to see how far you understood the concepts. That is very important. But as for now, it's just elementary questions. But maybe in the future, I might make a session specifically that we answer theory questions that is being given in our calculus book. Okay. So now I can't find my question. Here it is. Yep. Okay, this is nice. All right. One side limit. Oh, I haven't touched about one side limit. Okay. So wait, I think one side limit has something. At what point does the right limit exist? But okay, I could do one question. All right, I could do one question about one side limits. Okay, so okay, answer these questions. Okay, so we are given a question, right? Before I enter the trigonometry section, I would like to discuss the one side limits. So f of x. Wait, let me give you a picture about what I'm talking about first. Let me graph here. Then let me give you this, right? So this rate indicates the endpoints. Okay, so let's assume that this function is continuous everywhere else. So what I'm going to talk about is what is this points? Okay, so basically, whenever we are dealing with endpoints, when it comes for limits, this only exists approaching from the right, or in other words, right hand limit. Okay, right hand limit exists, but the left hand limit doesn't exist. Okay, but still, we can find the continuity by using the right continuity, I think, the right side continuity, meaning that limit as x approaches c from the right of f of x is equivalent to f of c. This also indicates that it is continuous. Okay. Same goes to when c is approaching from the left. This also indicates that it is continuous as well. But but in the future, when we discuss about differentiability, then that is a different story. For the theorems that we'll be using in the future, Rolle's theorem, in intermediate, intermediate value theorem, mean value theorem, extreme value theorem, and so on. So, but for now, know that the right hand side, as x approaches from the right hand side, and if both exists and both of them are equal, it is still continuous, but you call it as the right side continuity, I guess. I have to recheck about my terms that I'll be using, but this is also continuous. Therefore, f is continuous everywhere else on the domain. Okay, so okay, I'm gonna cover this. All right, let's compute this particular limit. They ask us for f of x. They give us f of x, a piecewise function, where a square root function, square root of 1 minus x squared in the domain, which is 0, from 0 until x, until 1, and 1 is less, 0 is included in this particular function. And then we have 2. where x is equal to 2. Okay, now the question asks, at what points, if any, does limit of x approaches c f of x exist? At what points? C. If any, does limit x approaches c exist? Okay. Limit x approaches c f of x. Okay. They want, okay, which points does this exist? Now, what are the criteria that we have to know to make sure that x approaches c exists? We have to know whether or not the left side and the right hand side is equal. Okay. If this is equal, therefore, the overall limit exists. Okay. So based on this function, they want us to find like the domain or the inequality where x is where for the c where limit x approaches a particular value c, f of x exists. That is the question. So as you can see here, these are the endpoints. And from here, we know that this from the left doesn't exist. This from the right doesn't exist as well. Limit as x approaches 0 from the left is not doesn't exist as long including x approaches 2 from the right, it also does exist. So what does this mean? What are the values of c where the overall limit exists? So I think this is answer. So let me write it down. So this is the answer, which is anyway, I think I did wrong. Wait, oh sorry. I'm very sorry, it'll be 1. Okay. Yeah, if any does limit x approaches 6. So first is from 0 until x until 1. Okay. And then from 1 until x until 2. So this indicates, I think that 0, 1, 1, 2. Why 1 doesn't include? Okay. Why is the value of 1 doesn't include? So as you can see here, let me drop this down. Okay. So what happens if limit as x approaches from the left of square root of 1 minus x squared? What happens? What is the value of 1? What is the value for the limit? Square root of 1 minus 1 square, obviously it becomes 0, 0. But what? Wait, no, I'm sorry. It's not left. Wait, it's left, right. Yeah, it's left. How about limit as x approaches 1 from the right? What is the function from the right? 1. So we know 1 is constant, then there will be no changes. So it's still 1. So what does this tells you? It tells you that as x approaches 1 from the left and x approaches 1 from the right, it's not equal. So this indicates that at x is equal to 1, the limit doesn't exist. All right, the limit doesn't exist. Okay, so therefore my inequality should be the one that I wrote just now. So let me check the answer. I usually check my answers because I really don't want to make any mistakes so that the viewers and my classmates here will not have any issues to understand. So let me find it real quick. 2.5. Oops. 2.3. Oops. It's not the one here. Here it is. This is question 9. Yeah, I'm correct. So limit as x approaches c, f of x exists on 0, 1, 1 to 2. Right, they're not talking about right hand side limits or left hand side limits. They're talking about the overall limit, which is x approaches c. They didn't put the notation plus or minus on our c, meaning that they want the overall limit, not the right hand side or the left hand side. Okay, and one doesn't include because I already showed you here where as x approaches one from the left, it's not equivalent to x approaches one from the right. Okay. So any questions on this particular question? Can I move on to the next part?
Yeah, I think I'm okay. Yeah.
Mhm.
See, me too.
All right. So that's about it. Basically, okay, as long as you know left and right, there should be no problem. Okay. Okay. So let's continue on with today's lesson, which is for trigonometry. Where I think yeah, here it is. Is it? Let's, okay. Yeah. Okay, there's this particular question I want to show you. It is very interesting if you want to compute it. So, mm, 19, question 19. So, question 19, they give us, for question 8, they give us limit as x approaches 0 from the right for absolute function of sine of x over sine x. Okay, so from the right. So as far as I know, right, my Dr. Wong did mention that all we have to do is just create the absolute value of sine of x. Okay, so it becomes sine of x for, where is my calculator? Right, let me create this pivotal function first, and then we could substitute the value. Yeah, so this is for x is larger equal to 0, and for negative sine of x, it should be x is less than 0. So since this 0 is approaching from the right, therefore, we are taking this particular value. So x approaches 0 from the right, indicating that sine of x over sine of x, this should get 1. Okay, we know that sine of x over x is 1, and a constant will not change anything, and therefore our limit is equal to 1. Okay, so I hope you guys have no like sorry. Wait, let me check that. Sine of x. Wait, let me try another way, because I don't think that this way is really practical, because yeah, sine of x is between -1 and 1. So okay, yeah, I think this is better lah. So okay, -1 sine of x 0 and then okay lah. Okay, as for now we use this lah. Okay, we create our piece function, then we evaluate from there. Okay, but I think that will be it should be better lah. Yeah, or we could do this. We know that in a range from 0 x pi over 2, we know that the values of sine of x is always larger than 0, right? It's always larger than 0. And if I graph it out, let me check. Yeah, if I graph this out, I mean, graphing is really good if you guys know how to graph. So this is pi, negative pi over 2, and this is pi over 2. So at sine 0, oops, sine 0, it'll be 0. So here, okay, and like this, right? So give me a brief moment. Let me compute my limits here. Sine. Okay. So let us put here negative pi over 2. Here should be -1. Here should be 1. So here's the points and just connect. So sum. Okay. Oops. It looks like something else, right? Okay. All right. So based on this graph, right, as x approaches from the right, closer and closer to 0, we are using this is for modulus sin of x. Okay. So we know that for this particular range from 0 and x pi over 2, sine of x will always be bigger than 0, no matter what, as long as is in that range. And we know that 0 from the right is in this range, right? It's in this range. Therefore, the modulus of sine of x is equal to sine of x. That's basically it. Okay. Is 0 inclusive? Wait. Until we check whether it's inclusive or exclusive. Then sine. It's okay. Wait, let me create a better precise function. Hold up. So we know that 0 x until pi over 2 sine of x. Then here we know that negative pi over 2. Wait, let me rephrase everything here. So negative sine of x from negative pi over 2 x. We know that sine of x is from pi over 2 x pi over 2. Yes. So let's say that the reason why I'm using this range is because, well, x is approaching 0. So I'm trying to find on which interval the sine of x is always larger than 0 and sine of x will always be less than 0. Because now we are dealing with trigonometric functions. So we have the way we are dealing with modulus function is going to be very different. It's going to be very different because as we know, sine of x will always be between -1 and 1. Ejaan, ada a message. Yep. Right. Okay. That's one. Okay. -1, meaning that the absolute maximum is 1 and the absolute minimum is -1. Okay, it's in this range. So right now I want to know on which range for my x values when sine of x will always be negative and when will sine of x will always be positive. So here is the particular range. I'll be putting in this lah. Okay. Between negative pi over 2 and until pi over 2. So from here, based on the range that I am been given, as x approaches 0 from the right, then it will be sine of x. But what happens if x approaches 0 from the left? Negative sine of x. Okay, so that's about it. Then you could solve the limit from there. So is it that how's it? My explanation. Do you guys need more of it? Oh yeah, you guys have more questions.
think wait. Yeah, I think it's okay. For
Okay.
it's
Yeah.
just to
Uh,
us, like, since it's coming from the right, so we're only focusing on the right side, but then because we're dealing with absolute and like the modulus sine x, we need to look at both sides, is it? Like the negative sine x and then sine x.
yeah. We have to know when will sine of x will be negative and when will sine of x will be positive. Yeah, we have to know about that part. We're not dealing polynomials anymore. We are dealing trig functions. Yeah, so that's going to be a bit
Okay,
a bit
okay.
difficult.
Yeah, yeah. Understand.
Yeah, because there will be a particular function of trigs. It will always be positive, But how do we know? That is an important part. Lah. That is why
Oh.
we will be using this inequality, negative sin of x between -1 and 1. Yeah.
Okay, okay.
All right. How about you, Putri? Hopefully you understood.
I'm okay.
Okay, yeah, right. Because I might make a small test for us, honestly, for limits in the future. Lah. But I will not be using the questions from Thomas Calculus books. I'll be using another source of which James Stewart Calculus books. So yeah, I'll be using that as my source to create questions, and then in the future I will be distributing to you guys. Okay. All right. So now, um, it's a difficult part for me lah, but okay, I believe that we could do it. No problem. So we're given a particular limit as x approaches 0 from the right for 1 minus cosine x divided by cosine x minus 1, but the absolute function. All right, so okay, maybe let's try and find the range for cosine x. So generally speaking, -1 inclusive, cosine x is inclusive 1. So I want cosine of x minus 1. So I minus 1 both sides. Okay. And then I simplify it to become -2 between cosine of x minus 1, 0. Okay. So what does this tells us? What do you guys think? Can cosine of x be positive at some particular point? Does it give a positive value for cosine of x when we substitute x values?
I mean, it's between -2 and 0, so no,
Yeah.
right?
Yeah. But now we have a modulus function. What does the modulus function tells you? Or absolute function, sorry. What does it mean for any values inside of it? What does it turn into?
So then it'll be positive, lah, right? I mean,
Yes.
all
Yeah.
right.
Yes. So now we are okay. Now that's correct. Very correct. So how do we make it to be always positive, but in a different form? Yes. Now that is the question that I'll be showing you. So in other words, since we know a modulus function will always be positive, and we know that the range of cosine of x minus 1 will be this, indicating that it will always be negative. Therefore, oh yeah, and I think this, yeah, -1. So it's cosine of x, right? Yeah, let me check that. When will it be 1? Oh, 0. To that. Okay, so on cosine of x is 0. Okay, when x is 0, cosine of x will be 1. As I know, yeah. Cosine of x will be 1. So wait, let me do f of x. Okay, f of 0 will be 1. Okay, f of x meaning that cosine of x minus 1. Okay, so all right. Wait, let me, what happens to 1? Okay, so 1. Oh, wait, I don't want that. I want, yeah. So when x is pi, what happens? When x is pi, that will be -1. Yeah, no, sorry. It will be -2. But I want to know when the value will be 0. All of that. Cosine. So 1 will be, betul lah. Yeah. Sorry, this is 0. So this is the values of x that we'll be dealing with. Okay, but I will not be like plus 2 pi k. No, that is generally speaking. But I will be focusing on these 2 points, meaning that as far as I know, between -pi, no, 0 x pi, yeah, 0 x pi. So between these particular points, I'll be focusing on, because these values should give me the range. So when x is 0, it gives me 0. Okay. gives me 0. So when x is pi, that it gives me -2. Okay, so that is correct lah. So in this range, whenever we substitute x values in this range, meaning that the cosine of x minus 1 will always be negative. Okay, so let me try another one, cosine 2 pi. Yeah, okay. But I'll be focusing on this range only. So, but why am I focusing on this range? Because it has 0 in it, meaning that the limit wants us to find where x is approaching 0 from the right? So when x is approaching 0 from the right, cosine of x minus 1 will still be negative, meaning that it will be like this. 1 minus cosine of x divided by negative for cosine of x minus 1. Okay? This down here is similar to up there. Both of them are similar. Both of them still gives us a positive value, meaning that I didn't change my definition of an absolute function. Absolute function will always gives us a positive value, right? But down there, the reason I made it in that form is because I want to simplify it. But the reason why I can't simplify it from here is because of this absolute function. I can't just simply simplify it without defining it at that particular function and at that point, which is x approaching 0 from the right. So, okay, so from here, I could, expand the brackets to make it in this form. 1 minus cosine of x over 1 minus cosine of x. I could simplify it, and as usual, it becomes 1, therefore the value is 1. All right, is it correct? Please tell me it's correct. Yeah, it's correct. So it's 1. Okay. Wait, it's pi. Pi over 2, 0. Yeah. Sorry. Yeah, it will be less than 0. Okay. So generally speaking, right, for all values of x, cosine of x minus 1 will always be 0. It will always be a negative value. So if I write my function here, then when x is 0, then it's 0. Okay, so 0, 0. When it's pi, it's -2. Sorry, positive pi. If it's negative pi, then it's -2 as well. So here it is, like this lah. Oops. Something like that in a way. So this graph shows that it will not output a positive value. It will always be negative. Therefore, by adding that negative sign, it is also true if we add the absolute function. Okay, both of them are equivalent. Okay, so hopefully you guys understood on how to evaluate this kind of limit. It's really interesting because we can't use the old-fashioned way by creating a piecewise function and then selecting the inequality where x approaches from the right or from the left. From here, you have to know at which point does cosine of x will be negative, at which point where sine of x will be positive, negative. Okay, vice versa. Right. So, any questions? That's the interesting, really interesting. Any questions?
Yeah. Wait, yeah, I do. So wait, back to the, I think the second line for the, like you put the negative for cos x minus 1. Yeah, I just want to make sure I understand clearly the negative part. You put it there because you want to just simplify the cos x minus 1, the first one, right? The beginning of it, right?
Yeah. We know that this part here will always give us a positive value. Okay, fine.
Yes.
So I want to make it in a sense where both of them are similar, but from here I could simplify it by expanding my negative value in my negative sign, and then I could simplify this expression to become a simple.
So basically, you want to make it equivalent, that the values
Yeah,
will be
yeah,
positive.
yeah.
Okay, all right.
I'm just defining my absolute function to become this form so that I could like simplify and evaluate the, because if I directly substitute 0 from this limit here, I will get the indeterminate form, right?
Yeah.
0 divided by 0. So how am I supposed to evaluate it if I can't simplify it? So I tried to define my absolute function in this form. From there, I could simplify it, and from there, I could evaluate it very, very simple.
Okay. I think I understood. Yeah.
Good to know.
I
Oh,
have a question also.
okay.
Uh, the one yang for the cos x punya interval tu, like memang you have to choose from -1 to 1 ke?
Um, yeah, that's basically it for sin of x, for cosine of x. Both of them have the same absolute value and the absolute minimum. Yeah, absolute maximum, absolute minimum. Both of them have the same.
Okay.
So yeah, if I share my screen for decimals, okay, let me share on my tablet lessons here. Um, okay, so let's see for sine of x. Um, where is it? Okay, y is equal to sine of x. Yeah, here. So we know that the values, the absolute maximum will always be 1, and the absolute minimum will always be -1. Same goes to cosine of x. So let's see cosine. So cosine of x is similar. The absolute value, absolute maximum for cosine of x is 1. The absolute minimum is -1. Okay.
Faham? Right. And then one more question.
Okay.
Yang bawah tu kan, then we choose x equal to 0 and x equals to pi kan. Is there any reason?
Because our limit here shows that x approaches 0 from the right. So I just want to give myself an interval where this is true, where for all cosine of x will always be less than 0, meaning that cosine of x, but we evaluate, sorry, cosine of x minus 1, yeah. This particular expression will always be 0 for all values of x in that interval. Yeah. So I'm just stating that, okay, in this range that I am focusing on, since it has something to do with my limit, x approaches 0 from the right, okay, cosine of x minus 1 will always be less than 0. And then, and then you could see when we graph it, okay, let me show on decimals, make it simpler. When we graph it, y is equal to, yeah, so as you can see, the values of cosine of x minus 1 will always be less than 0 or less than equal to 0. So it will not be a positive value in a way. But I pick a specific range, which is I think between uh, 0 and I think it's pi over 2,
Yeah, it's pi over 2.
or is it pi?
Pi over 2. Eh,
Isn't
yeah,
it
pi.
five?
Yeah,
Yeah.
it's pi. So yeah, I picked this range just to show that cosine of x will always be less than 0 lah. Yeah, because it's something to do with my limit, since limit is approaching 0 from the right. So I'll be saying that, okay, in this range, since it is something to do with absolute minimum and absolute maximum, then this particular range of x will always give my sine of x, a cosine of x will always be 0. Yeah. Okay. Cosine of x minus 1 will always be 0 in that particular range. But as I can see, since cosine of x and sine of x will always be a consistent graph, like it will be an oscillating graph, like this. So it's really simple to find the pattern. If you pick a specific range, then other range will follow, will be the same. But I think it would be better if I define it as 2 pi, like this, like 2 pi. Yeah, I think that would be better. But yeah, I'm not sure if anyone from YouTube wants to give a better explanation, then please do. Okay. But yeah, that's about it. And that's very important when you try to evaluate trig limits.
Alright, thank you.
Hopefully hopefully I explain it in the correct way. That's my goal. Okay. All right. So let's move on to. Okay, I will not be teaching you guys greatest integer function because I myself haven't. So I'm sorry about that because there's a proper way. We can't just evaluate it directly and then get that particular value. I have to like, yeah, since this is a one-side limit, then yeah, that's the thing. Okay. All right. Now for the best part of evaluating limits, which is this limit as x approaches 0, okay, sine of x over x will always be 1. Same goes for the other limit, which I have to find. Where is it? Here you go. Cosine limit as approaches 0 for cosine of x minus 1 over x will be 0. Yeah. But if you want me to prove that is true for this one, okay, by using this, I think I can now. All right, let me try. Okay, so we know that cosine of x can be evaluated from 1 minus 2 sine square x over 2. We can evaluate cosine of x through this identity. So, okay, limit as x approaches 0 for sine of x, yeah, oh no, for sine square x over 2 over x over 2 square. Okay, so wait, sine of x. Oh wait, I can evaluate it in a simpler way. Okay, wait, no. It's an it's the other way around. Okay, I would like to prove that this is true. Okay, so limit as cosine of x minus 1 over x. Okay, so from here, we know this is the same as this, right? So, okay, I'm gonna express it in sine square x over, no, I'm just gonna leave it there. Wait, sine square. Yeah, square. Yeah. So this will be 2. This will be 1 minus cosine of x. Wait, sorry. Negative 2 sine square x over 2 is equal to cosine x minus 1. Okay. We know that this term is similar to this term. So from here, we can evaluate it to become negative 2 sine square x over 2 over x. Okay. So limit, okay, x approaches 0. We know that we could make both of these terms in this form. Okay, and then we know that sine square x means that sine x times sine x. So we could express it in this form: sine x over 2 negative sine x, and I'm going to put it up here. Sine x over 2. Okay, then from here, negative by using one of the limit laws for product operations. So it would be like this: sine x over 2 over x over 2 times with limit x approaches 0 for sine x over 2. So we know that this this is from this particular limit. Therefore, we can substitute it to become negative 1 times with sine x over 2, or sine 0 will be 0. Therefore, this is 0. So that is the proof. Okay, so that is the proof. Okay, hopefully you guys have no issues about that, because I'm afraid that doctor will ask for proofs like theorems, identities, formulas, and then differentiation. So all that is really important. Okay. All right, now let's compute limits by using that information. So question 23, they are asking for a limit as x approaches 0, sine square root of 2 theta over square root of 2 theta. Honestly, right, if you want to change it, wait, why is it x? It's theta, theta. But as you can see, okay, let me make it a different, I'm gonna change this theta, will be u. Okay, so when theta, wait, no, square root of 2, yeah, square root of 2. Theta is equal to over, okay. So if I evaluate this correctly, it will be limit. Okay, so as theta approaches to 2, this is similar to square root of 2 approaching to 0, sorry, 0. This is equivalent, this implies that my u, wait, what is mu? Okay, u approaches 0 as well. So this indicates u approaches 0 sine u over u. Okay, so this will be, we can evaluate this limit based on the previous identity, I guess. Is it identity? I want to use the right term for it. Yeah. Oh, sorry, theorem. It's a theorem. Since we already proved it. Okay, yeah, theorem. It's a theorem. Yeah, based on the theorem, which is limit as theta approaching 0 for sine theta over theta, where is equivalent to 1. So based on the theorem, we could evaluate this limit simply as 1. Okay. But if you guys don't want to waste your time, just know that if this is similar to this, then you could use the theorem. Right? Just use that kind of information, because the other side, they assume that you know that you do this. So if you know that both of the terms are similar, square root of 2 theta over square root of 2 theta are similar, then you could use the theorem. Okay, no problem. Okay, any questions so far before I continue on with yeah, another question?
Those two are the theorems lah, right? The sine x over x and then cos x minus
Yeah,
x.
yeah, both of them are theorems. Yep.
Oh, okay. And then for sine x and x, there's no, I mean, there's a proof for it, right? But then that's like, oh, because you only like discuss the proof for cos x minus 1 over x, right? Yeah.
Yeah, yeah. If you want to, yeah, sine theta over theta, the proof, right? I think it's true. They graph it. Yeah.
Oh,
They,
okay, fine.
oh, they use the sandwich theorem.
Ah, I see.
They use this. Okay. Sandwich theorem.
Mhm.
Yeah. Limit is x approaches 1 over theta. Jan 0.00001. Yeah, it becomes bigger. -1. 0.0001. -1000. Good job. I really want to. Wow. Okay, I can prove this using sandwich theorem. Okay. Yeah. I want to try that. Sine x is between -1 and 1. We know that -1 over x, distance sine of x over x, 1 over x. So from here we know that limit as x approaches 0 for -1 over x. It's not infinity, is it? No. Oh, it's ah. Okay, it's not. Oh, it's radian. Okay. 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 So yeah, how do I show up? Because we are measuring in radian, right? Radian. So, but
Yep.
later lah. Later I'll show you. Later I'll share the proof lah. Because I didn't study that much about proofing.
All right, noted.
Yeah, but they did mention that you could prove it by using sandwich theorem, which is nice. Okay,
Uh,
so I want to see what question is really difficult. This one. Okay, so for question 37, we are given a limit as theta approaching 2 for sine theta over sine 2 theta. Oh, by the way, if I like, I'll be ending the class about 5 or 6 minutes. But if you guys have other things to do, let me know, because I'm afraid that I'll be taking your time. It's your right to use your time well. Okay.
All right.
Okay. Thank you. So from here, limit as x approaches 0. We know that sine to theta, we have the identity where sine to theta can be evaluated as 2 sine theta. Oops. 2 sine theta times with cosine theta. Okay, we know that is the identity. So we could resubstitute sine to theta becomes 2 sine theta cosine theta. Okay. All right. It's not x theta. So we could simplify it. We could make it tangent. We could find that value there. But the question wants us to use the theorem, which is as limit theta approaching 0 for sine theta over theta, then you don't want us to just simply evaluate it from there. So we have to use this method. Remember the limit law for multiplication. That is what we will be applying here. So first, I'll be separating this term to 3 parts. Okay, which is sine theta. Wait, let me, yeah, this, I'm gonna leave it. Constant sine theta, 1 over sine theta, and 1 over cosine theta. The reason why it's important is because we will be using theorem. So how do we apply the theorem? So first, look at your theta here. It's theta, right? There is no coefficient in front of it, 2 theta or 5 theta. No, it's just theta. So what do you do with it? You multiply by 1. What's that? What does that mean? It means that you do this. Limit theta approaching 0, 1 over 2 sine theta times with 1 over sine theta times with 1 over cosine theta times with theta over theta. Now, why am I multiplying by theta over theta? This is because I'll be distributing this particular term to my respective terms. Now, how do I do that? By doing this. Sine theta over theta times theta over sine theta. Because we know that both of them are equivalent. It still gives us our um, this previous form. It's the same. Because theta over theta is 1. But here we don't simplify it. We just let it as it is. And then by using one of the laws, limit theta approaching 0 for 1 over 2 times with limit theta approaching 0 for sine theta over theta, and another one which is limit x approaching to 0 for theta over sine theta, and another one which is limit as x approaching to 0 for 1 over cosine theta. So the question is, what is this limit? What is the value of this limit? Now, I'm gonna prove that just a short moment. So limit as x approaching 0 for x over sine of x. So this can be evaluated as limit x approaching 0, 1 over sine of x over x. And by using the limit laws as well, limit as x approaching 0, 1 over limit as x approaching 0 for sine of x over x. So by using the theorem and by knowing that for a constant, it will still be a constant, it becomes 1 over 1. It becomes 1. So what does this tells you? It's basically saying that limit as x approaching to the theta for sine of x over x is equivalent to limit as x approaching to 0 for x over sine of x. Both of them are the same. Okay? So from here, we know that we could evaluate this limit very easily. So this will be 1 over 2 times with 1 times with 1 times with 1 as well. I guess 1 over cosine theta should be 1. Yes. So from here, our final answer should be 1 over 2. Tada. So for question 37 is 1 over 2. Yep, that is correct. But the scheme, right? They want us to use sine to theta, but okay, no problem. Let's assume that you do not know this identity. So what you should do is you should do this. Red color. This is the alternative. Limit x approaching 0, sine theta over theta times with 2 theta over sine 2 theta times with 1 over 2. That's the alternative, and this is true as well. It will give us a value 1 over 2. So either way, both of them will gives us the same value. Okay. So any questions so far? Sorry if I talk too fast, but yeah, that's how we solve the limit.
I'm good. Wait, you put the theta over theta to just to simplify lah, right? To rearrange and then so that we can use the theorem.
Theorem, yes, very
Okay.
true.
So okay, you don't put the theta over cos theta because it doesn't make sense. I mean, just
It doesn't evaluate anything.
yeah, okay, fine. So you just put the theta and theta at the places where it's supposed where you can make okay,
Yeah.
fine.
So that I could use the theorem. Yeah. How about you, Aisha? How about, so far so good?
I think okay kot.
Okay, good to
Sekejap.
know.
The one yang last kali tu kan, yang 1 over cos theta tu.
Yeah.
That one we just evaluate lah. X
Yeah.
equals to 0.
Yeah. It's not undefined. It's not indeterminate form. Nothing really weird. It's just 1. So
Alright.
yeah,
Okay.
just the 1.
Oh.
Okay. All right. So it's already 10:10. I'm taking a lot of your time. So yeah, I will be making part 3 just so I could evaluate more limits. And then I'll be preparing a small test and I'll be discussing with my friends if I am very committed to it, inshallah. Okay. So do you guys have any? But we haven't covered for cosine of x minus 1 of x, but inshallah we will cover that part in the future. Okay. So any questions so far from both of you?
Nope, I'm good. Thank you.
All right. How about you, Aisha?
No from me also.
Okay. So I've been thinking, right? Since for MATLAB, I've been thinking I want to discuss the assignment with you guys, because yeah, I don't know. I just want to discuss and I want to see can I explain very well. So what you guys want to discuss assignment or what?
Yeah, sure. But I want to try doing it first. So maybe we can set a time or day date or
Mhm.
time where we can, where we can
I agree with Farah.
yeah.
Mhm. Okay. So both of you can discuss the time and date and everything, and just let me know in the group when do you guys want to do it. Okay.
Alright.
Bye. Noted.
All right. So as usual, happy holidays. Enjoy your holiday on Monday. Okay. Use it very well. Right?
You too.
All right.
Bye. Thank
Okay. See you
you.
later. Bye bye.
Bye.